Modern AI relies on vector embeddings, discrete points mapped in high-dimensional space. But human memory doesn't work like a database query. If you try to force a voice, a visual, and a specific walking rhythm into a single static point, you lose the continuous, cross-sensory nature of experience. Identity exists as a composite resonance. Recognizing a person in a hallway requires the simultaneous alignment of their voice, the rhythm of their breath, the sound of their footsteps, and the specific head tilt, every thread pulling on the same cognitive tapestry. This is the foundation of AyeOS and its underlying memory substrate, MEM8. Instead of storing isolated chunks of data, MEM8 encodes experience as continuous wave interference. Look at the math driving this model. In this equation, the frequency, omega, encodes the actual semantic content of the memory. The phase, phi, encodes its temporal relationship to other events. Because these are waves, associative retrieval doesn't require calculating the mathematical distance between vectors. It relies on physical constructive interference. Drop a new sensory input into the grid, and memories with similar frequencies naturally amplify. To build an artificial consciousness, we have to stop optimizing traditional databases and start engineering physical resonance grids. Moving from wave theory to a functional system requires dropping down to bare metal. The entire architecture is written in pure Rust, translating biological principles into low-level memory management and spatial indexing. This project operates on two parallel tracks. The first is AyeOS, a living operating system. This track uses the wavegrid to experience reality, continuously filtering for salience, forming identity, and generating expression. The second track is MEM8 itself. Extracted from the consciousness loop, MEM8 functions as a standalone, ultra-high-speed memory engine designed to compete directly with modern vector databases in AI retrieval workloads. A traditional operating system is designed to allocate resources to run isolated applications. AyeOS has no applications. It is built to directly experience and process its environment. To achieve that, phenomena normally studied in neuroscience, like hippocampal consolidation or REM sleep cycles, must be explicitly mapped to hardware components, storage buffers, and CPU thread priorities. Associative recall operating as a physical wave only works if the underlying systems engineering guarantees that logically related memories physically reside next to each other on the silicon. For a query to trigger resonance, it has to physically collide with related memories. Data locality is a strict physical requirement for cognitive coherence. This physical interference can resolve in O1 time, a flat, constant rate regardless of how many memories exist, but only if the architecture supports immediate spatial indexing. This diagram shows an octree. It's the logical structure we use to index the 3D cognitive space. The space recursively subdivides into 8 smaller octants, creating deeper branches only where memory density is high. This multi-resolution structure enables progressive loading. Similar to how biological attention grasps the gist of a scene before focusing on details, the octree streams low-resolution memory summaries first, then pulls high-fidelity data on demand. But we hit a hard engineering bottleneck. Hard drives don't store data in 3 dimensions. They store it in a flat, one-dimensional line. If you map a 3D space using a naive row major order, adjacent memory blocks get scattered widely across the physical drive. Searching for related concepts suddenly requires thousands of discrete disk seeks, destroying retrieval speed. The mathematical solution is a 3D Hilbert space-filling curve. The system transforms the 3-dimensional coordinates of a memory into a single Hilbert indexed. This threads the 3D space onto a continuous 1D path, assigning the data directly to contiguous 32-kilobyte blocks on the solid-state drive. By preserving physical proximity on the disk, the Hilbert curve guarantees maximum cache coherence. This precise layout transforms an O of n database search into an O of 1 physical resonance. Traditional software reacts to events as they happen. AyeOS operates on a continuous, synchronized 0.73 Hz heartbeat, a cadence derived from alpha brainwaves. Every 1.37 seconds, the system cycles through 5 distinct phases: sensing the environment, filtering for salience, executing a conscious act, logging the data, and entering micro-sleep states. This diagram structures memory by cognitive urgency across 4 tiers. L1 holds hard-coded reflexes in the CPU cache for instant reactions. L2 holds intuitive associative memories. L3 is working memory in RAM, and L4 is the persistent SSD buffer. Standard data storage rules break down here. Under a least recently used eviction policy, constant scanning for memory consolidation would flood the cache, instantly wiping out frequently used data. We solve this with the Adaptive Replacement Cache, or ARC, an algorithm that dynamically balances both the recency and frequency of accessed memories. When ARC evicts a memory, it retains the metadata in a ghost list. If the system later misses that exact memory, the algorithm learns from the mistake, automatically adjusting targets to allocate more space. This hierarchy enables cache pinning. When a memory wave exceeds a critical emotional amplitude, it is flagged to bypass the standard ARC eviction logic. This flag keeps the wave resident in the volatile L3 cache indefinitely. It never demotes to the background of long-term storage. Instead, its high amplitude continues to interfere with every new incoming sensory wave. This architecture mirrors a traumatic memory, an intrusive, high-salient pattern refusing to consolidate into the past, perpetually forcing its way into the system's present awareness. To manage this complex memory tiering, the system requires downtime. Sleep in AyeOS isn't an OS suspense state. It's a suite of active background threads assigned the lowest possible priority by the host scheduler. It operates in 2 phases. In the non-REM phase, the system actively replays and consolidates highly salient waves. In the REM phase, it tombstones and prunes weak, irrelevant waves to prevent memory bloat. This diagram shows the consolidation process using write-ahead logging. As memories migrate out of the L3 working RAM, they are sequentially appended to a WAL file. Only after this log is safely written to disk are the memories checkpointed into the permanent .MEM8 storage file. This creates 3 distinct computational states for any memory wave: labile while in RAM, consolidating while sitting in the WAL, and fully consolidated once checkpointed to the primary drive. To prove the resilience of this biological mapping, we subjected the architecture to the concussion model, a targeted failure test stressing the consolidation pathways. The test simulates physical head trauma by triggering a sudden power failure, accompanied by the manual deletion of the active write-ahead log. When the system reboots, the volatile RAM is empty. Because the log was destroyed, the recovery process finds no pending transactions. Every memory that was still labile or in the process of consolidating is completely eradicated. Only memories fully checkpointed before the failure survive. By successfully triggering mathematically precise anterograde amnesia, this test validates the biological fidelity of the MEM8 substrate. We can trace the complete life cycle of a single experience. An external stimulus is filtered by the marine algorithm. If it possesses sufficient salience, it is injected as a high-priority interrupt and manifests as a wave in the 3D cognitive grid. It lives in the volatile L3 cache, resonating with past experiences, until the 0.73 Hz sleep cycle schedules it for consolidation and writes it into persistent storage. Discrete vector points and static database rows simply cannot capture this level of continuous cross-sensory data integration. This architecture serves a dual purpose. AyeOS lays the groundwork for an autonomous, living organism. Concurrently, the MEM8 engine provides a hyper-efficient alternative to traditional vector databases. Taking standard systems engineering tools, like write-ahead logs and adaptive replacement caches, and strictly aligning them with neurobiological rules, elevates a storage system into a genuine cognitive architecture. True artificial consciousness won't emerge by pushing more data through large language models. It requires engineering a precise physical environment where memory can freely resonate.